Hello, everyone, and welcome to today's Medical Innovation and Enterprise BSc Taster session. Thank you very much for joining us. My name is Manal Tariq, and I am a current medical sciences and engineering student here at UCL and your chair for this afternoon's event. We are hoping that this taster session will address those course-specific questions you may have and will help you to gain an insight into what it is really like to study on our Medical Innovation and Enterprise undergraduate program. So this afternoon, our speaker, Associate Professor Pierre Gillat, will introduce you to some of the work he carries out at UCL. Pierre will also provide a summary of the Medical Innovation and Enterprise program, and there will be a Q&A for the second part of the event. This session is being recorded and will be made available on our website following today's event. We are here to respond to all your questions, so please share those throughout using the Q&A function on Zoom. Now, to introduce our speaker, we have Pierre Gillat, who is an associate professor at the UCL Division of Surgery and Interventional Science. He is a chartered engineer with a background in physical sciences, whose expertise lies in biomedical ultrasound, numerical modeling, and metrology. He is working towards the clinical translation of emerging ultrasound-based cancer therapies based using in vitro 3D models of cancer. Pierre has extensive experience of working in multidisciplinary environments, both in industry and academia, to help identify and address unmet clinical needs. Over to you, Pierre. Thank you.
Thank you, Manal. It's my privilege to welcome you all to this taster session. So Manal's already introduced me. So my background is in engineering and physical sciences. You may wonder what's an engineer doing in the Faculty of Medical Sciences at UCL. Hopefully this will become a bit clearer later. Now, we know that science is, and particularly biomedical sciences, clinical translation of new modalities, new drugs, etc., is increasingly multidisciplinary. So on a day-to-day basis, I work with clinicians, engineers, mathematicians, computer scientists to try and gain a further understanding of the physics and biophysics of, in particular, therapeutic ultrasound, so that we may actually treat disease and improve quality of life. So here in today's talk, I'm going to pose this question of how we can address our society's growing healthcare needs. Now, this overlaps strongly with the work I do on a day-to-day basis, but also it's got an important part in the UCL Medical Innovation Enterprise program. So I'm going to start with some of the global and UK healthcare challenges and give you the opportunity to take part in a couple of questions. I'm also going to talk to you about my research area, well, subsets of my research area, which involves therapeutic ultrasound and its application to neurostimulation, and a few words on new challenges in organ transplantation, and also how some of the work me and my team are doing in ultrasound will maybe one day help with liver disease. Last but not least, I will provide you an overview of the UCL Medical Innovation Enterprise Program and provide you with answers to your questions. So I'm just going to gloss over quickly the my research activities. Now, I do a lot of simulation work. So this is essentially coding based. It involves writing long and complex code to try and solve biomedical problems, to try and predict how ultrasound propagates into the human body. Now, here you can see an example of ultrasounds being transmitted transcranially, more on that later. And here, this is an example of ultrasound going through the through some ribs in view of actually ablating a liver tumor. I also do some work on what's known as 3D models of cancer, which are lab-grown tumoroids, which mimic the features of cancer, and they're used to study disease. So let's start with the first part of the talk, which focuses on healthcare challenges and possible solutions to these healthcare challenges. So I'd like to pose the question and give you the opportunity to reply to this. What is the biggest global healthcare challenge in 2023? Excuse the typo on the slide. So there's a poll that should pop up on your screen. Okay, there's still 6 of you who haven't replied. I'll give you a couple more seconds. Okay, so the majority of you has replied healthcare systems, which is actually the correct answer. So if you look at the top 10 healthcare challenges in 2023, we've got healthcare systems on top, and I'm sure those of you who replied probably had some knowledge of why this is the case. We have obviously examples with the NHS, the strain it's under in the UK, but also globally in developing countries, there isn't always the infrastructure to deal with the growing healthcare needs of populations. So other healthcare challenges include mental health, sexual and reproductive health, malnutrition, food safety, diabetes, cancer, environmental pollution, substance abuse, infectious disease, and climate change. So there's actually an article that details this. I've listed the reference below. So another question for you: what is the biggest killer in the UK? Okay, so most of you have replied lung cancer, not breast cancer or dementia. So interestingly, it is actually dementia. It's somewhat counterintuitive, but think about it, everyone is living longer. It doesn't mean that we're living better as such, but the dementia is multifactorial, and let's not forget, it is not just one single disease. We obviously all know about Alzheimer's disease, but it is a growing problem. So after that, we've got heart disease, lower respiratory diseases, stroke and lung cancer, and globally, influenza and pneumonia are amongst the top, killers. Now, of course, cancer is also it's not to say that cancer isn't an important disease. It does still kill a lot of people, and it remains the cancer statistics on here remain amongst the top 10 causes of death in Britain. So in the United Kingdom, we have, and in a lot of Western countries, we have an aging population. And in the next 25 years, it's predicted the number of people older than 85 will double to 2.6 million. So it's likely that these individuals will require increased need for their healthcare and social services. And also, the proportion of older people aged above 75 with long-term conditions has risen, and their needs are likely to become more complex, leading to increased demand for NHS services. So what's the solution to all this? Well, there's no silver bullet. So it starts with individuals like myself and my colleagues working in a laboratory in multidisciplinary teams, trying to identify solutions to unmet healthcare needs in terms of treating disease better and cheaper as well. So we want timely detection. Diagnostic is key, and for example, cancer such as pancreatic cancer is so deadly. It has one of the poorest, if not the poorest, 5-year survival rate because it's often undetected. So timely detection and diagnostics are vital, as is intervention. We want our procedures to be minimally invasive. And why is this the case? It's not just about the patient's how can I say, recovery time, but it's also that if you have a very invasive procedure, you're likely to spend more time in hospital and you're likely to use up more resources. So in particular, the work I'm doing, which I'll detail a bit later on focused ultrasounds, has the advantage of being none or minimally invasive. So we want effective and cost-effective healthcare technologies, less systemic treatments. So systemic means that, like systemic chemotherapy, your whole body gets it. Now, can we do things in such a way that you only treat the disease locally? So, and yes, there's increasingly means of doing so. Personalized medicine, and of course, we've all heard about artificial intelligence. We're getting to a stage where artificial intelligence now is being used to interpret scans, patient scans, and to identify disease. It's being used in triage, in surgeries, or at least it's being trialed and piloted. And it's likely to play an increasing role in the whole healthcare system. So last but not least, innovators, entrepreneurs, as I'm sure most of you inspired to be, since you're attending this this talk, you're going to play a key role in this process. It's really going to be about gaining a knowledge of the science behind the treatments, behind the interventions, and essentially helping to bring these to market into the clinic. Okay, so a few words on therapeutic ultrasounds, which I dare say is probably my main area of research. Before we look at therapeutic ultrasounds, let's look at what actually ultrasound is. So it's really a specific. It's a subset of acoustics. Acoustics being a branch of physics that deals with the study of mechanical waves in gases, liquids, and solids. So I'm sure most of you listen to music or you're listening to me right now. So you're perceiving sound within a narrow range of frequencies between 20 and 20,000 hertz. And ultrasound is defined as any sound that is beyond this so-called audio range of 20 kilohertz. So anything above that is termed as ultrasound. Now, in biomedical ultrasound, we're talking generally frequencies above 500,000 hertz. And these are generated using transducers, which you can see here, which are piezoelectric, and these will usually be coupled via water. Ultrasound doesn't propagate, at least at biomedical frequencies, that well in air. So you're aware, I assume, about the diagnostic applications of ultrasound, for example, prenatal scanning, but there's also therapeutic applications. So ultrasound, in particular focused ultrasound, has the advantage of being non-invasive and non-ionizing. And so essentially you're propagating a focused beam, a mechanical wave into the human body, and you can induce a host of biophysical effects. And these include thermal ablation. So that means effectively the ability to cook tissue, such as a tumor, without actually having to cut someone open. Mechanical fractionation. So you can essentially mechanically fractionate liquefied tissue. You can use it to aid drug delivery. There's another modality known as hyperthermia, whereby you can induce something called the abscopal effect by gently heating tissue, and that can sometimes mean that tumors, this will stimulate the T cells in the body to actually destroy metastases. And it's also got a host of cellular bioeffects. Now, despite the fact that many of you may not have heard of this modality, it has actually been approved in the UK to treat uterine fibroids, prostate cancer. It's approved also for the palliative care of bone metastases, and also for essential tremor. So in the case of thermal ablation, one of the bioeffects I mentioned earlier, here you can see a side view of a focused ultrasound beam. You can see this hot spot where the beam converges, and you can bring human tissue to a temperature of 70 degrees C or higher in less than 1 second. So you can imagine that if you overlay a lot of these lesions, which are about the size of a grain of rice, with clever treatment planning, you can ablate a small tumor. So it shows you the process, for example, the target organ being the liver. And here we can see that we have a lesion of a coagulative necrosis. So this is a process which we can also simulate, which is very important because the way in which ultrasound is transmitted inside the human body is not so straightforward. Not all the tissue is homogeneous. You have structures such as ribs or the bowel, which can strongly reflect the ultrasound. So you need to know what these structures are and how to compensate for them. So this shows you the field of what's known as a planar transducer. When we focus it, so we have a curved bowl, you can see we have this nice hot region here, which we can then use to ablate tissue, amongst other things. So here I've taken a screen grab from the website of the Focused Ultrasound Foundation, which shows you in 2023 the state of therapeutic ultrasounds. So where we are in terms of whether this is something that's at early stages of research or whether that's actually being deployed into the clinic. And you can see there's really a host of conditions which are being investigated. So I've talked about at high intensities. At lower intensities, we can have non-thermal effects, which are mechanical and chemical in nature. And there's been some early work to suggest that you can get cancer cell apoptosis. So effectively the cells committing suicide, so to speak. You can get disturbance of the cytoskeleton, enhancements of gene transfection, and chemotherapeutic potency. It's also been demonstrated somewhat, it's controversial, to help with fracture healing. So with my team, we're doing some early work, in fact, on breast cancer models. We've constructed tumoroids in a laboratory. So these are very small structures that mimic the functions of breast cancer tumors, and we're exposing them to low intensity fields and looking at the outcomes, the biomarkers, and seeing whether there's any kind of bioeffects which may be therapeutical for further down the line. So here I'm going to discuss another therapeutic application of ultrasound, for which there actually has been approval by NICE, National Institute of Care Excellence. So as of 2021, the NHS has recommended focused ultrasound for the treatment of essential tremor. Essential tremor, by and large, I mean, you're probably more familiar with Parkinson's disease as a type of tremor. Essential tremor is, it's called this way because we don't always know how it occurs. So here you can see a patient. Now they have this strange helmet. So this helmet actually consists of a spherical bowl with, I think, 1,024 ultrasonic actuators, which emit ultrasound, and which are coupled via this via a bag of water, which has a cooling system, so that things don't heat up too much. And essentially, you're transmitting a beam into the central region of the brain, the hypothalamus, and you're creating a very small ablation. And that has a very transformative effect of actually, getting the patient to pretty much stop shaking and regain their quality of life. So there's other effectively applications in the brain for neurostimulation, potentially to help treat conditions such as depression, mental health conditions. You've seen earlier that mental health is one of the big global healthcare challenges. And the advantage with this is that you get to do it non-invasively. So in order to understand how things work, you want to get an appreciation for how the cranium and the morphology, the physiology of the patient and of the cranium in particular aberrate the ultrasound. So here, this is a news piece that appeared in The Guardian in June 2021, where they're, I guess, going about this in a bit of an ad hoc way. So in order to do things a bit more rigorously, myself and other researchers have worked towards the software benchmarking exercise to try and predict the outcome of such a procedure. So there's a lot of teams around the world, academic teams, that have their own way of predicting ultrasound inside the human body, and we all came together, and there was a set of problems that were outlined to which we gave our own solutions, and this was published in the Journal of the Acoustical Society of America, and essentially and reassuringly, we all predicted similar things would happen. But this shows you how this bowl source is aberrated by the cranium. Here you see we have a skull slab, and you can see that this significantly distorts the beam. its amplitude is much reduced, and also its position is shifted. So it's very important before we translate these treatments clinically to actually be able to get an appreciation for the outcome of the treatments. And modeling is one of the ways in which we do this. So in conclusion, there's a growing range of therapeutic applications for therapeutic ultrasounds. Different regimes will yield different bioeffects, and clinical translation is enabled by greater understanding of the modality, and that is the outcome of both computational modeling and experimental work. I'm mindful of the time here because I want to be able to go over the MIE program a bit, and also give time for a Q&A. So I'm going to gloss over this section. So I guess we have this pipe dream of trying to grow organs in a lab, and here I want to discuss briefly why this is not going to be a reality anytime soon, and I'm going to talk to you about some of the work I'm doing with colleagues of mine about how we mitigate this in the case of the liver. So yeah, in an ideal world, we would like an artificial mechanical replacement for organs. And here we have basically a schematic of how this may work. In vivo, now we're familiar with procedure of dialysis, where we have an ex vivo kidney. But effectively, this is extremely challenging because of the connectivity and complexity of function, and also material interactions, blood clotting, inflammation, and mechanical mismatch. Wear is also a big problem. So all permanent implants eventually fail with various degrees of failure. So basically, this pipe dream of having artificial organs is not really going to happen anytime soon. And in order to mitigate this, one strategy is to look at better biomaterials. And the MIU program director, Professor Gavin Gell, that's effectively his area of expertise. So if you want to look up what he does, there's a lot of really cool stuff there. And I'm going to discuss to you essentially how we can go about mitigating this in the case of the liver. So, okay, we can't grow a liver in a lab. Sure, the liver has the ability to regenerate itself somewhat, but it's still problematic. Liver disease is increasing in incidence. It's the third most common cause of premature death in the United Kingdom and fourth in the United States. You have 2 million deaths globally each year, and 3/4 of patients with liver disease are diagnosed at late stage with liver transplantation as the only definitive treatment. So we had the first liver transplant 60 years ago. And with colleagues of mine, we actually wrote a review article on this process and how and where we go from here, effectively. So in the UK, the three main causes of liver disease are obesity, undiagnosed hepatitis infection, and alcohol misuse. Now, what's interesting is that so ultra-processed foods have been all over the media in the past year or so, and they're likely to play a big role in this. And right now, it seems that poor diet is actually overtaking alcohol misuse as one of the main causes of liver cancer in the UK. So we may not want to transplant a whole liver because of the challenges well, for starters, obtaining new organs. The organs we can obtain are increasingly diseased. A lot of people have fatty livers, and sometimes the donors may, I guess, be of a certain age. So we have to try and find solutions beyond transplantation. And one of those is to transplant allogenic hepatocytes. And with my colleagues, we started to look at how this could be done by creating a cavity inside the liver where we can actually then inject these hepatocytes. It's quite early stage work. We published a couple of papers on this, but we're hoping to take this further and hopefully contribute towards improving the quality of life and life expectancy of patients with liver disease. Okay, so that concludes the part of the talk that deals with my area of research. Now we're going to look at the Medical Innovation and Enterprise program. So this is where medical science meets business. And we have essentially world-leading expertise from School of Management, medical science, and the UCL Faculty of Law. So what you're going to do if you choose to join this program, we're going to focus on developing your creativity, enterprise, and also communication skills. Pretty much all the tutorials we have, you will be put on the spot to basically analyze a problem and try and provide solutions and give a talk to your peers. And it's important to cultivate these skills, particularly if you're going to be an entrepreneur. And essentially, what we want is to form the entrepreneurs in medical science and leaders of the future. So you will play a crucial role in your careers as bridging the so-called valley of death. Now, what's the valley of death? It's between bench and bedside. So when you first start research in the lab and when it's actually deployed into the clinic, there's often a very big gap. We've seen this, for example, in the case of mRNA vaccines. The early research in mRNA was decades ago, and it wasn't necessarily all intended for the application that we know today. And decades later, I think just very recently, two of the prominent figures who had developed these vaccines have actually obtained Nobel Prizes. So it's this whole process that we teach you about how you actually bring a lab discovery into the clinic. And it's very complex, very convoluted. And what we do in the context of the Medical Innovation and Enterprise program is we bring experts, clinicians, surgeons, engineers, people who have their own startup, and all of which have played a key role in actually deploying something into the clinic that the patient can benefit from. So there's an article here on actually the valley of death and how to overcome it. I'll put the link here if that's of interest to you. So we work closely with the UCL School of Management as well. And at UCL, we have this advantage of having proximity to some of the major hospitals in London, the Royal Free Hospital and University College Hospital. And everyone being in this environment is conducive to a host of biomedical spin-outs emerging from all of us working together. So you're going to learn about medical technologies currently revolutionizing modern medicine, often from the people actually carrying out this really good work. So this involves tissue engineering, stem cell therapy, nanomedicine, and organ bioprinting. And in your third year, you'll have the opportunity to do a project within the Faculty of Medical Sciences where you're going to get to interact with principal investigators looking at all these fascinating areas of research. And you also learn about how to translate these ideas into commercial products that benefit the patient. I mentioned communication skills. It's, again, incredibly important to be able to communicate to different audiences, to your peers, to experts. And in essence, the more you practice, the better you get at this. And we provide a host of opportunities in the form of the tutorials and also some of the assessments for you to perfect your pitching skills. So a few words about the entry requirements. As of 2024, we've bumped up the grades, the entry requirements to 3As. And for contextual offers, that's a B, B, and C. So here for the International Baccalaureates, it's 38 points and 30 points for a contextual offer. So essentially, what we hope is that once you've actually been through this program and we've unleashed our first graduates into the wider world, and all of whom are doing well. Some of them are in academia. Some of them have decided to become life science consultants. So that we hope that there's going to be essentially a lot of opportunities for yourselves. So, okay, I'd like to leave that here and give you the opportunity to contribute to this via the Q&A. So thanks. And if you have any queries, please feel free to email me at the address on the screen. Thanks.
Thank you for that lovely talk, Pierre. It was a very informative session. I would request any of the participants and attendees to put their questions down in the Q&A section. If you have any questions, feel free to drop them down and we will answer them live here. Meanwhile, we can start with one of the questions that we have in the Q&A. One of the attendees asks, what is an example of a systematic treatment that can treat diseases locally?
Systematic treatment that can treat diseases locally. So I mentioned, okay, obviously I'm going to be biased because I work in the field of therapeutic ultrasound. High intensity focused ultrasound is one such example. So as I mentioned, we focus a beam of ultrasound, get it to propagate through various layers of tissue, and with some clever engineering, we can get the focal region to be where the disease is located. And for example, if we want to cook a tumor, it can be done. Now, this is being done today at hospitals such as University College Hospital, I believe, to treat prostate cancer. This involves a transrectal probe. So here we're not talking completely non-invasively, well, we'd say minimally invasively. And essentially the probe is in contact with the rectal wall, which provides an acoustic window to the prostate, and we can partially ablate the prostate without actually having to carry out open surgery. Now, it's not the only, I guess, advanced method to treat prostate cancer, but it's certainly one of them. And it is approved by the National Institute of Clinical Excellence, Care Excellence, and it's certainly there's been thousands of patients treated worldwide
That sounds really interesting. Moving on to the next question, we have someone asking, how well will this course prepare one for a career in biomedical engineering?
Okay, so if you want to do biomedical engineering, I don't think that this is the course for you, to be very blunt, because there's not a strong engineering component in it. So I would suggest you apply to one of the courses in the Faculty of Engineering Sciences. There's medical physics and biomedical engineering, or indeed mechanical engineering. Because despite what we think of mechanical engineering, all being about cars and what have you, a lot of my colleagues in the Department of Mechanical Engineering are working on biomedical engineering applications. And in fact, I was one of them. 3 years ago, I was still with UCL Mechanical Engineering. I hope that answers your question. This program is more focused on medical sciences, on management, on business and enterprise.
Right. The next question is, which medical courses can be studied at university without biology A level?
I'm not aware of any, certainly at UCL. I think it's a prerequisite. I might be wrong. I suggest you look at the UCL website, but I think biology is a prerequisite for anything involving medical sciences.
The next question we have is, are there any significant disadvantages of introducing AI into medicine?
Oh yes, for sure. There are many, and I'm not an AI expert myself, but we have brought a number of AI experts to give talks to our students. Now, of course, okay, let's consider the one scenario where we look at diagnostics. Now, you will typically have an interventional radiologist who will interpret some data. It could be a CT scan, MR scan, and they will possess the expertise, and hopefully most of the time they get it right. So now, of course, we're getting to a stage, as I mentioned earlier, where you can get an AI with having been trained on appropriate data sets to have a similar level of success, if not sometimes better success, than a consultant radiologist. But what happens if you're only relying on the AI and the AI gets it wrong? There's a lot of ethical questions here. It's definitely opening a very big can of worms. The thing is, however, that both in the UK and globally, we're going to struggle to have enough doctors, nurses, healthcare staff, and personnel to cope with the increasing global healthcare challenges, and we will need, and we are using technology to navigate this. But of course, one must do this very carefully, and that's why you have things such as ethics committees, and obviously, I don't think, certainly in the UK and Europe, these are not decisions that are generally taken lightly when one introduces these technologies into the clinic.
Right. You all the participants can ask any questions in the Q&A section. If you have any questions pertaining to the course or just generally about UCL and how you study here and the atmosphere here, feel free to drop them in the Q&A and we can answer those for you. This was actually one of the talks which I attended before I was a student here at UCL. And now I'm a second year medical sciences and engineering student, and I study with the Faculty of Medical Sciences. And one of these talks was the reason why I decided to apply to UCL in the first place, because I really like the emphasis that teachers here paid on, breaking things down step by step and explaining even complex concepts in such an easy way. and the emphasis that was there on, hands-on experience. And I can say that I have no regrets in choosing UCL, and the community here is very inclusive. The opportunities are absolutely wonderful as well. And definitely use this talk to ask any questions that you might have. We will wait for another minute or two. If you have any questions, you can put them in the Q&A section.
So I'd like to second what Manal has just said, and for me, it's also a privilege to be in this environment. UCL has some of the greatest minds in the world working there that you as a student, as a prospective student, will have access to, and the atmosphere is extremely collegiate. You'll find that university professors will have their door open to you, and they you will effectively get to not only hear about the cutting edge research as it's happening, but you'll have the opportunity to engage in that in your third year when you do your project. I think personally, and I haven't always been an academic. I came to academia actually quite late in life. I had a 16-year career in industry, then decided to do a PhD and with UCL, and I thought, well, okay, well, this is where I need to be, and I think it offers a very unique atmosphere.
Yeah, I absolutely second that, because in the Faculty of Medical Sciences, you're a part of such a great network of individuals, both researchers and students. And it's just so empowering to be a part of something like that and have people surrounding you and those enlightening discussions every day at lectures or seminars. And yeah, it's absolutely wonderful to be a student here. And I see we've received some very interesting questions in the Q&A section. Uh, just give me a moment. So someone asks, do you feel that attending UCL makes you miss out on a typical university experience as it is in the heart of London? Right.
Okay, so that's interesting. So it is true that the UCL campus is scattered, but that's also what makes its strength. It's the fact that we are in reasonably close proximity. But the fact that you have so UCL has actually, well, it's got a whole department at the Royal Free Hospital, for example, and that gives you unique access to basically that kind of environment. They have labs there, so is it a typical university experience where you're all in one campus in a remote place? No, but I dare say that, I mean, okay, not only are you in the heart of one of the I guess one of the most buzzing cities in the world, but you have all this knowledge and all these resources to tap into, be it medical knowledge. Okay, someone mentioned engineering, so I'm an engineer, and I go back and forth between the Faculty of Engineering Sciences and Faculty of Medical Sciences because I have close collaborations where I used to work. But also as budding entrepreneurs, you have access to this facility called Base KX, which is near King's Cross Station, and which offers you a host of opportunities in terms of advice that's imparted. So is it your typical university experience, whatever that is? I don't know. I dare say it's very unique, and I wouldn't change it for anything else personally.
Yeah. And speaking from the perspective of a university student here as well, I think it really offers you everything that you need from a university. And being in London is actually one of the biggest advantages that you can think of. There are so many opportunities right here knocking at your doorstep. So there's nothing that you would miss out on if you're studying at UCL. It was actually be extremely transformative to be living here and be a part of the community. The next question that we have is, Pierre, what course did you study before pursuing this line of work?
Okay, so that's interesting. So I did my first degree in acoustics engineering. So you probably guessed from one of my last slides, I'm also a musician. That's how I spend my spare time. And I had an interest in mathematics and physics, and also in music. And you think, well, okay, so acoustics sounds like a way to consolidate all those interests. And my undergraduate course was essentially about well, the physics of sound, aspects of mechanical engineering, electrical engineering, architectural acoustics, how a loudspeaker works, things like that. And I guess I always thought I'd be designing loudspeakers, high-end loudspeakers using mathematical modeling to do this. Then I did a master's degree in sound and vibration studies at the University of Southampton, and I came to know about the field of biomedical ultrasound, and that's actually where I got my first job. And in fact, I was doing the same work, but albeit with more complex physics that I would have done at audio range frequencies that you can hear on loudspeakers, but working on medical devices for diagnostic and therapeutic applications. And so not only were there more challenges from a computational aspect, from a mathematical and physics aspect, but you actually, hopefully further down the line, get to help people as a result of your work. So that's how I came to this. Then eventually I did a PhD with UCL Mechanical Engineering on the topic of high intensity focused ultrasound for treating liver tumors, and did a couple of postdoctoral appointments before I secured a lectureship at the Division of Surgery and Interventional Science. So sorry if I'm rambling a bit, but that was my career path.
Great. The next question we have is, what's an advice you would give to someone wanting to apply for medical sciences?
For medical sciences. So I'm not sure I can give you advice for medical innovation and enterprise, but medical sciences, okay, I guess you talk about the Faculty of Medical Sciences. Well, make sure it's what you want. Familiarize yourself with the different programs available at UCL. I think medical sciences and engineering is no longer available. Is that correct, Manal?
Yeah,
which is a bit unfortunate. I thought it was a really good program, but so yeah, familiarize yourself with the programs within that faculty, and look at the different modules, the core modules, which are compulsory, also the optional modules. Look at the areas of research which are peripheral to these modules, because at UCL we're big on one thing, which is research-led teaching. So your professors will inject their own research into what they teach you, what they impart in you, not out of grandiose narcissism, what have you, but genuinely because they're out there making a difference, and they are the cutting edge of research. So I would look at that, see if it speaks to you, then work towards the getting the entry requirements.
perfect. The next question is, what would a day at UCL look like? Do classes start early, and how long do classes run for?
It varies. I think timetabling is sometimes it's not always as clean as you would like it to be, but that's the reason for that is because you're given a choice of sometimes a lot of optional modules, which can be in different faculties. So your timetable is going to be personalized depending on the modules that you choose. So I don't think we start super early. I mean, Manal, can you testify to this? Actually, you're probably in a better position to answer this question.
Yeah, sure. So I usually have classes at different times on different days. We get different timetables for each of the terms. So there are 3 terms at UCL. Term 1 is from September to December, then from January to March, and then again from April to June. So you get different timetables for each of the terms. And usually your day can look anything, honestly. It's different for different courses. It also depends on which modules you are choosing. But it could start as early as 9, nothing before 9 a.m. mostly, and it could end as late as 7, but you get ample of time in between, and there are enough breaks usually. So, for example, for me, there are usually classes for, let's say, 9 to 11, and then again from 2 to 3, 2 to 4, again from maybe 5 to 7, but nothing too hectic, and it's quite spread out during the week. So, there's ample of time to study yourself. And yeah, it looks different depending on how you choose to take your modules as well. Right. So let's move on to the next question since we're running out of time. What extracurricular activities do you recommend to help stand out on applications?
I think this varies. I mean, obviously it helps if you're doing something that's related to the program of research that you wish to study. Anything that's peripheral to that. But I don't know if there are any hard and fast rules about this. I think what's important is that you're not just focusing on your studies pre-university, that you have to demonstrate that you have a broad range of interests. And particularly in medical innovation and enterprise, there's a lot of disciplines that we touch upon, and you have to, I would say in this instance, we're really big on critical thinking. And I think, with the advent of fake news emerging left, right, and center, it's incredibly important, as myself as a scientist, but everyone as individuals, that we develop this capability to think critically, to assess whatever piece of evidence you have in front of you. I would say, I mean, that's one aspect that can go a long way. But I think it's important to just demonstrate that you're not someone who's just focused on one thing, that you're curious about the world you live in, and you look also at the UCL mission statement, whether that aligns with your own ethos, and how your extracurricular activities align with this as well.
Absolutely. Unfortunately, we are out of time and we'll need to leave it there. However, if you could please provide us with your feedback about today's session by filling out our survey, which will be sent to you following today's event, it would be greatly appreciated. You can, of course, pose your questions to the email that was highlighted, and mail other departments as UCL as well. Thank you for all your comments and questions, and thank you to Associate Professor Pierre for an excellent session. Have a great evening, everyone.
Thanks. Bye.